Welcome to Unit 8, Stoichiometry. In this unit, we will be covering molar mass, dimensional analysis, and significant figures. So, what is molar mass? Molar mass is the mass of grams in 1 mole of an atom or compound. So, in other words, when you have 1 mole of an element, the amount of grams of the element you have equivalent to that mole is the molar mass. In the periodic table, you can find the molar mass of individual atoms. In Unit 2, we learned about the atomic mass. If we look at the atomic mass of oxygen on the periodic table, it is 16 AMU. The atomic mass is equivalent to the molar mass. In 1 mole of oxygen, there are 16 grams. 16 grams is the molar mass of oxygen. So now let's get into dimensional analysis. Dimensional analysis is a structured way of helping you convert between units. In order to be able to do dimensional analysis, remember you must have a conversion factor. A conversion factor is a ratio of equivalent measurements. For example, 1 meter is equal to 100 centimeters, or 1 kilogram is equal to 1,000 grams. A way to think about dimensional analysis is picket fences. This picture gives a brief example on how to set up a conversion equation with the given value and the conversion rate. To set up the equation, you put the given value multiplied by the conversion rate. You write the conversion rate with the units desired or what you are trying to convert to as the numerator. To calculate, you multiply the numbers on the top and divide by multiplying the numbers on the bottom. Let's take a closer look at an example. Okay, let's try to convert 6 centimeters to kilometers. Let's start with the picket fence. Remember, the given value 6 centimeters takes the first spot. Next up, we write equivalences. In other words, the conversion rates. To convert centimeters to kilometers, we first need to convert centimeters to meters, then meters to kilometers. So we write the conversion rates needed. 1 meter is equal to 100 centimeters, and 1 kilometer is equal to 1,000 meters. Next, we turn our conversion rates into fractions. As you can see here, the first conversion rate, 1 meters over 100 centimeters, is written with the meters on the top and the centimeters on the bottom. This is because our given value is 6 centimeters, so we write 100 centimeters on the bottom. Notice that the values circled in green are in centimeters, and one is on the top and one is on the bottom. This means we cancel out centimeters and end up with just meters. Next, we write 1 kilometer over 1,000 meters because we are trying to cancel the meter values to end up with kilometers. The meters circled in red will cancel out and leave us with the final result of kilometers, which is what we want. Here is a closer look at that. After we plug in the conversion rates into the picket fence and solve, we cancel out the centimeters and meters in the conversion rates and end up with just kilometers. To calculate, we multiply all the numbers on the top and multiply all the numbers on the bottom. After doing 6 centimeters times 1 meter times 1 kilometer over 100 centimeters times 1,000 meters, we get a grand total of 0.000060 kilometers, which can be rewritten as 6.0 times 10 to the power of negative 5 kilometers. The last concept you need to understand is significant figures. Significant figures help us know how many decimal places our answer should have after doing calculations in chemistry. But first, there are 4 important rules. The first rule of sig figs is leading zeros, which are zeros before a non-zero number, are not significant. For instance, in the number 0.00508830, as shown below, all the zeros before the non-zero number 5 are considered insignificant. The second rule is zeros between non-zero numbers are always significant. As shown below, the 0 in between 5 and 8 is significant because it is between two non-zero numbers. The third rule is trailing zeros, which are zeros after non zero numbers, are significant only if there is a decimal place. So in the number below, since there is a decimal place and the last zero comes after the decimal place, it is considered a trailing zero that is a significant figure. And lastly, the fourth rule constants are infinitely significant. Any non zero number is always significant. This is because a constant is something you can count. For instance, this picture shows 3 pencils, not 2.9 or 3.1 pencils, but there are exactly 3 pencils. So 3 has infinite sig figs, and in any case, a constant is always significant. Let's take a look at some examples. 45.8 has 3 sig figs because each digit, 4, 5, and 8, are constants, and remember, constants are infinitely significant. The number 0.003456 has 4 significant figures. Remember, the zeros before the non-zero number 3 are not significant because they are trailing zeros. The digits 3, 4, 5, and 6 are significant because constants are infinitely significant. Therefore, this number has 4 sig figs. The number 3.4006 has 5 significant figures because all the constants are infinitely significant. The two zeros are in between constants, so they are also significant, totaling to 5 sig figs. Now, why don't you give it a try? Here's the number 5200. 5200 has 2 significant figures. 5 and 2 are significant because they are constants. The two zeros are trailing zeros and are not constant. Now, what about 5200 with the decimal point at the end? This would have 4 significant figures. As always, the constants are significant. This time, the zeros are also significant because there is a decimal point in the number. And lastly, what about 563.000? This would have 6 sig figs. 5, 6, and 3 are constants, so they are significant. The three zeros are trailing zeros, but since there is a decimal place, they are considered significant. In total, there are 6 significant figures. Now that you are an expert at counting significant figures, it is time to apply them to calculations. Firstly, the rules for addition and subtraction are the answer should have the same number of decimal places as the number with the least number of decimal places. Here are some examples. In the first problem, we keep one decimal place because 7.3 is the decimal with the lowest amount of decimal places, since it only has one decimal places while the other decimal has 9 decimal places. For 15.679 minus 8.5555, 15.679 has 3 decimal places while 8.5555 has 4 decimal places, so the final answer 7.126 is written with 3 decimal places. Now for multiplication and division. This is where you get to apply those significant figure skills. The rule is that the answer should have the same number of significant figures as the number with the least number of significant figures. Let's take a look at two examples. 14.657 has 5 significant figures since all the digits are constants. It is multiplied by 0.0548, which has 3 significant figures, since the zeros are leading zeros and are not significant, while the rest of the digits are constants and are significant. So the answer 0.803 is written with 3 significant figures after rounding. Let's verify this. 0.803 has 3 significant figures, with 8 and 3 being constants and the 0 being in between the constants. Another example is with division. 7.2034 has 5 significant figures, and it is being divided by 5.640, which has 4 significant figures. The answer is written with 4 significant figures, which is 1.277. Great job on this lesson. Be sure to practice using significant figures when writing and rounding answers after calculations. Also, be sure to understand the concept of molar mass and practice dimensional analysis when converting between rates. Thank you for watching.